Good afternoon, class. In today's video, what I'd like to do is to give an introduction to thermodynamics and all of the concepts that you're going to need to understand and wrap your head around this very important but also very misunderstood concept. So, one of the ways that I like to define thermodynamics is that it is how a group of particles deals with energy entering or exiting the system. Now, of course, there are various vocabulary words that we need to discuss in this one, and so that's why I underlined them with different colors. So first is group, and the second one is system. So let's go over what a group is. A group is the behavior of individuals which can be different from the behavior of groups. Now, a group is a several particles of a generic variety. So it could be hydrogen, it could be water, it could be people. These are all what would define as groups. Now, one of the things that makes this, especially this whole thing, this thermodynamics concept, very difficult is actually this word group, because in the word group, it implies that there is a behavior that is not necessarily shared by each individual particle. For example, if I had water, let's say, I could drink water and it would keep me alive. I could spray water on my face and it would keep me cool while I'm exercising. However, if I had an ocean of water, it would crush me. It would kill me. I couldn't even drink the whole thing because my body doesn't even have the capacity to hold that much water inside. So, as a group, water can be very dangerous, can be very deadly. And yet, in a small amount, it's actually life-giving. So that's why the understanding of how a group works versus how individuals work is very different. And up until about this point in physics, we've been dealing with individual particles and their physical attributes like momentum, energy, force, motion. All of those things are based on the individual particle that we've been dealing with. Now we're talking about how groups behave. Also, one of the other things before I move on from groups is that even with water, as in my example of water, deep below the ocean in the mid-Atlantic ridge, there are volcanoes. The continental plates are separating, and there's a lot of lava coming up, or magma coming up through the continental plates, making this vast array of volcanoes underneath the ocean. Magma is incredibly hot, and yet you never see steam bubbles coming up from the mid-Atlantic region. And the reason why is because normally, under normal circumstances, like here at the surface of the Earth, when water gets really hot, it turns to steam. However, as an example of how group behavior can be different, if you have miles upon miles of water, which is like tons and tons of water on top of an area, there's so much pressure that the water molecules actually cannot turn into steam. They would stay as water. It can be as hot as molten lead down by those in that mid-Atlantic ridge, and yet the water is still liquid. So keep in mind that this is where we're headed in this introduction to thermodynamics. The behaviors that you would expect, especially in our everyday lives, may not be true when we deal with a collective group like we have in these. So now we have to talk about a system. And the system is going to be the one that's going to really, I find this one to be the one that's going to be the thing that's going to be like the big blind spot in thermodynamics, and especially in thinking about thermodynamics, because this is where I have to bring in my props, because to understand a system, you have to understand it's not just the particles that you're talking about. It is also the container, the volume that contains those particles is actually very important to get to some of the thermodynamic principles that are dealt with anytime we deal with groups of particles. So what do I mean by that? So you've got the total number of particles in a container with a certain volume. So I gave two examples here. One is a closed system. As you can see, it's just a circle that contains not just the words closed system, but also a few dots. Then I've got an open system, which is open over here. So some of these particles can leave if they feel like it. If there's ever a reason for them to exit, they can. And so I'm going to go over, using my props, a few of these examples. So, oh, and also just so you know, some of they're more technical terms for these. You could have this closed system would be basically a permeable system. That's another way of, that's a more higher level of way of saying it, because it's permeable because things can flow in between. So an example of that would be like the cells in your body, and how water can flow into the cell, it can flow out of the cell, especially with red blood cells delivering oxygen. Oxygen can flow into a red blood cell from the lungs, and it can flow out of the red blood cell when it delivers it to the other cells in your body. A closed system would be something that is not permeable. It's not, it doesn't enter, things don't enter it at all. I mean, or at least if it did, it would take a whole lot of work, because the system is not set up to allow for that kind of transfer of particles. An example is your skin, because your skin should be impermeable to most germs. However, the skin is not really a good example of this because of a purely closed system, because your skin does allow water to go through, because we are mostly made of water. So in this case, so even though it may be a closed system to dirt and outside germs, it's actually permeable to other things like water and even air to an extent. So just to keep in mind, closed and open systems, these are definitely things we need to think about. Also, and because I just gave that as another example, there's also what we call a semi-permeable system, which you can have particles flow one way, but not the other way. And I'll show you examples of each of these things using my props. So for example, oh, and I'm sorry, one more thing. Systems and the volume that they can contain, there are different properties that are based on how flexible the system is. So as we will go into it, now it's time to bring out my props. So first I'll start with a milk jug. As you can see, I can deform this milk jug and it makes a sound. It has just the milk jug itself has a property. It has a certain volume, it has a certain permeability. Right now it's basically impermeable to anything trying to go in. But if I take off the lid, now what happens is this becomes an open system. So we had a closed system, nothing goes in, nothing goes out. However, now that I've taken off the lid, it is now a permeable system. It is now open. So because now if I pour it, let's say, that means water or liquids, whatever is in here, can flow in and out. So that would be a closed system and an open system. And this is open in both directions. Then you have something, let's say like this. Let's say I have a spray bottle like this. This is a closed system, again, because nothing goes in or out. But this would be a better example of something that we would call a semi-permeable system, because as you can see, whatever's inside of the spray bottle can leave the spray bottle, but it cannot enter it very easily. Obviously, even with this milk bottle, even with the milk jug, I could still have stuff enter the system, but it would require energy. So one of the things that one of the words that I'll be throwing around with thermodynamics is this idea of something where it would naturally flow. There would be a flow of particles one way or another, and it would be the natural flow of something. So it basically means that given nothing else, if I do something to a system, what will be the behavior of the system to correct itself? For example, let's say like I said, if I did something to this to the milk jug, like when I compressed it like this, as you can see, I've bent it a little bit. So the natural response of the system would be to just stay like this because it's deformed. If I put in a little bit of work, I can fix it. Or I could even have, let's say I take a water bottle like this. This is very impermeable. It has no, it's also very rigid, so I can't, so if I squeeze, I am putting a little bit of pressure on it. I am deforming it a little bit, but as soon as I let go, it goes back to its original shape. So that's an introduction to how thermodynamics works, and also how some of the terms are going to be used, especially when I go over some of the laws of thermodynamics. This is going to come into play quite a bit when we're going through them, because how things like how energy flows through a system, whether it flows in or out, whether the volume expands or contracts, based on the conditions that are set out, are going to be very, very important in order to figure out what is going on in the system and how it's actually going to behave. So that concludes the introduction to thermodynamics. Good luck in your studies, and may the force be with you.